Hello, awesome, thank you. Excited to give this talk. This is gonna be a little bit different. I'm gonna give a talk on a research tool that hopefully that people here will find useful, especially if you're trying to develop human-centered AI. And it is something called Nisobirel. It's a Python library for human subject experiments with reinforcement learning environments. I'm just gonna fix this real quick so that I don't keep looking up. So I haven't used the Windows computer in like a decade. So I'm rusty here. Okay, great. And then okay, there we go. Okay, cool. Yeah, I tried to, put this over here so I could see this. Okay, so the kind of problem motivating this project was how do we easily scale human model comparisons, human AI comparisons? A bit about me is I came from machine learning. I did my PhD in deep reinforcement learning. And then after doing that, I was really interested in developing cognitive science models where you want to build a model and compare it to humans. And I learned when I entered cognitive science that a lot of people in the world, they will have a domain for their model that's like in Python or C or whatever, and then they will rebuild that domain once again in JavaScript. And that just seemed like the most laborious, cumbersome process ever. And it didn't seem scalable for having many comparisons. And so one thing I sought to do was to make that process easier. And so to make it easier, I've created this library called Nisobirel, which leverages JAX to kind of circumvent some latency issues around having a server and a client, where the server uses Python, the client uses JavaScript. But it's the first tool that lets you use a growing body of machine learning environments for human subject experiments. So you can look at planning environments like chess and Go. You can look at multi-agent environments like Tara of Hanoi or Tara of Hanoi. There are robotics environments that are written in JAX as well, and even like these 2D Minecraft environments. I'm gonna do one fix just to help myself. There we go. Okay. Now, one thing that's nice about this kind of tool is that now we can use the same code and the same data format for different environments, for both human data and model data, and with modern technologies like procedural generation or unsupervised environment design, this allows for automated design of tasks that test our hypotheses. Okay, so I present this tool to you. What kind of research does it afford you? So the first is, it lets you ask, this AI model that I've built, is it human-like? Does it perform, does it behave in human-like ways? And you can compare both humans and the AI. You can do this in both simple domains and also, where is this pointer? Oh, there we go. Oh, I see. But also more naturalistic domains like this 2D Minecraft. You can study human-compatible AI. So this is work from an ICML oral, where you develop an AI model and you see, does it collaborate with humans in ways that a human expects? Does it have social norms that people expect? And then also human-assistive AI. Now we can have a human that tries to do tasks in some environments, and you can see how well does, let's say, an LLM or a VLM, how well can it assist a human to do tasks, and how well does this support algorithm generalize across domains? Okay, so this gives you the outline for the talk. I'll basically go through some case studies, and the first one will be developing human-like AI. Okay, this is work with collaborators Sam Grishman, Sam Holigmaster, and Hung-Luk Lee. The question that we had for this work was, how do people generalize to new tasks and new environments? So consider moving to Harvard Square, like I did short 2 years ago, and you have experience going, is it possible to just mirror these?
It's a presenter, it's a extend.
I see that it's not possible, okay.
Can you say click or pointer?
That's fine, okay. Okay, so let's say you live here and you go to these two coffee shops. Now, given this experience, you can generalize to, let's say, getting a sandwich at either one. You can also generalize to going to this grocery store, even though you haven't really been there. Even kind of more excitingly for us as people, we have the ability to generalize to this using only partial observations of a large world, right? So this is Google Maps, but really this is what you see. You see what's in front of you, and you navigate the world through that. So what are some candidates for studying this kind of generalization? The first option is going to be reinforcement learning or caching-based solutions. And the basic idea is that you have some prior experience where you do things and you learn policies. Policies are probabilities of selecting actions given states. And you learn expectations for what those policies lead to. So you might learn that the first policy leads to great coffee, but okay sandwiches, whereas the second policy leads to okay coffee, but great sandwiches. And then when you want to generalize to like something new, you're going to reevaluate these policies for that new goal. And for example, that second policy might be good for whatever you want. Now, the pro of this is that it's very efficient. Because you have this cached expectation, evaluating it for new things is very quick. But the con is that this only explains how we generalize within our direct experience. So we can generalize, for example, to going to the grocery store, but that's not within our experience, and so it's not really explained by this caching solution. The other option is model-based or planning-based solutions. And the idea here is that people plan iteratively with some model of the world. You kind of imagine going to the grocery store. And if you have a good enough model of the world, you can make plans to kind of arbitrary things. So the pro of this is that it's very flexible, but limitations are that it's very expensive. So imagine, I'm new here to Pittsburgh, so it takes time to think about going from here to my hotel, et cetera. It's an iterative process that kind of grows in how much computation based on the length of the plan. And then you have errors from my model of the world. And then finally, learning a model of the world is also very hard. Okay, so now I'm going to ask the audience, which do you think better predicts how humans generalize? So the task is to get groceries. You start here. This is a juncture off of your known experience. The first option is that you plan at the beginning, and then you kind of follow reactive behavior following your plan. Second option is that you kind of vaguely know the way to go to get to the grocery store, and then once you get closer, you start planning. And the last option is that you don't plan at all, and you just have reactive behavior the entire time. If you think it's option one, could you raise your hand? Few people. If you think it's option two, could you raise your hand? Okay, nice. The majority of the people, that's great. If you think it's option three, could you raise your hand? One person. Two people. Me as well. Okay, so let's say, option three. So this gives a puzzle. How do we get planning-like flexibility with caching-like speed under real-world constraints like partial observability? And I'll tell you the thesis of the talk and the punchline is that brains preemptively solve problems with a multitask pre-play learning algorithm. We replay prior experience, let's say going here, and then we'll pre-play, accomplishing tasks that were accessible but not achieved, and then we cache the results. And so by preemptively learning about tasks, we have that available later on. Okay, so we study this in a simple domain where you can navigate around it. There's a train object and a test object. You can move up, down, left, right. And then there's a structure where this is optimal for the train object, this is optimal for the test object. Now I'm going to just go very quickly through this result, just to show you what you could do. So the result is that multitask preplay best explains human biases and response times. So this is a starting point. This is novel goal. Blue is if a person took a new path. This is a real person. Red is if a person reused an old path, like to the train object, but for this novel goal. We get a bunch of data comparing different models, planning models, humans, and then caching-based models. This is the pre-play. Humans are between planning and pre-play. So we can look at response times. You can collect response time data with NiceOverall. And then we look at when people take a new path, the response times are like this, high at the beginning and then flat. But if they take if they reuse an old path, the response times are flat. Argument to you is that when the response times are flat, that corresponds to this setting over here, where you basically are just following reactive behavior the entire time. You're not really planning. You're doing planning when you're doing this, right? So it helped us to adjudicate. So why was nice overall helpful here? Just summarizing it, this enabled comparing different AI models, including kind of state-of-the-art AI models. We were able to use response times to adjudicate between models that do more or less computation. And then we also generalized these predictions to this 2D Minecraft environment where you only have partial views of a large world with many objects. I'm not going to go through the details of this, but just shows you, here's a cog-sci question, want to build human-like AI, and we're able to get generalizable results using this tool. Okay, so I'm going to go on to another. Now for human-compatible AI. Okay, so here a question is, how do we build AI that generalizes to humans on new tasks and new environments without human data, right? We're going to be building AI, and it's great to incorporate humans in that process, and we should, but that is expensive. And so sometimes we want to be able to train without humans. So in prior work, the basic idea is that you have an AI that learns with many partners, a diversity of partners, and that had good generalization to new partners, including to humans. In this work, rather than having one AI trained with many partners, you have one AI trained with just one partner, but actually across many different variations of a task, right? So many ways that a task can manifest. And the basic finding of this work is that this allows for generalizing to the same partner in a new environment, but also new partners in new environments, including humans. Here are the collaboration results. So first thing I want to draw your attention to is that this is actually a baseline. This is our method. And the baseline does better for completing the task when generalizing with humans, okay? So I'm going to walk through the results along with what you can get from NiceOverall. We first are able to compare different multi-agent RL algorithms, including state-of-the-art ones, with human partners. We collected feedback after every episode from people while it was fresh in their memory. And what we learned was, so these error bars are tiny, but these are statistically significant. And what we learned is even though this AI completed the task more, our algorithm was preferred more by humans. We did both analysis. We used Likert scales, and we asked people, and we also analyzed the trajectories, and we basically learned that our algorithm was both rated as more human-like, but also it would collaborate more with humans. So this algorithm just did the task by itself, basically, whereas this algorithm would actually try to work with people. One takeaway from this is that just because a team of a human and AI will do the task more often at a higher success rate, it doesn't mean that they're collaborating. And this was something we found in this work. And then just, everything is saved, so you can do this kind of like analysis at the end. Okay, now I'm gonna touch on human-assistive AI. So here I'm gonna motivate a question. I will admit that I actually don't have super exciting results here. I kind of submitted this abstract, and then they were like, oh, here's, do you want to give a talk? And I'm like, all right, well, I guess I will. So how can we do basic research on an assistance paradigm that typifies everyday LLM assistance? So my argument to you is that a common setting we're in is that LLMs have encyclopedic knowledge across a growing number of domains, like cooking, math, physics, and we're increasingly relying on them as assistants and thought partners. So for example, I might ask an LLM, how do I start a business? And it'll tell me, oh, go to the bank, go to a bank to get this, go to Civil House to do that. I might take a photo of what's on my screen and say, how do I cook? Now, for both of these cases, we're in this interesting paradigm that I think is pervasive, where we act in the world and observe the consequences, but we can send messages to an LLM to get feedback where it has high domain knowledge. Right, so it's this asymmetric setting. So I don't have meaningful results to share, but I have this proof of concept demo of this that if you look up the paper, you can find it. But basically, there's an environment called XI Minigrid with millions of possible tasks. They're hierarchical tasks, so there's many things you have to do. And then there is this example setup where you control this agent. You have to figure out what to do you don't know, and you can ask an LLM for help, meant to be like a way of studying this asymmetric information setting. So if you are interested in this setting, please reach out to me. I'd be happy to think about this with you and think about what are some interesting questions we can ask here. And then, yeah, just to be clear, a human can control this, but also chat with an LLM here. Thank you for the time. Here is a GitHub, and I want to share that the GitHub has 11 example folders with working examples across all these settings, so which hopefully makes it easy for you to do this kind of work if you want to.
Questions? Cody, not surprising.
Just curious whether you have the data, the models, the human data also available here?
Yeah.
Okay.
Yeah, everything is saved and analyzable, both for my own work and for future work.
Okay.
By default, yeah.
Thanks.
Maybe one more really quick question.
I have this sort of abstract question, because it seems like there's this sort of tension between optimization and collaborativeness within a human AI team, because you don't want an AI to just do the whole thing and the human just watches, oh, that's a really good job. You want a sort of an adaptiveness. Is there like a goal to sort of have an ideal AI that's collaborative and optimal at the same time, or are these things separate and sort of tense?
Yeah, so like, great point. I think like where I hope the field goes is, so right now, like training, so one of the benefits of this is that it makes it easy to evaluate with humans. Now, because automated evaluation with humans has been hard historically, people that develop AI avoid it. But I think we can enter a paradigm where we have AI that trains with ostensible digital twins of humans on tasks, and you think about what are learning and decision-making algorithms that best support this digital twin, and then you evaluate that trained AI with new human partners. And then you are actually like designing and optimizing so that it's going to work better with people in the long run. I think it's not a given that that's going to happen. I think you need to have your evaluation like directly look for that or evaluate based on that. Yeah.
Let's thank our speaker one more time.